So when an ionic compound dissolves in water, that is actually an equilibrium process. There is dissolving of the ions that occurs, but there's also recrystallization of the ions. It's an equilibrium process. And so we can write an equilibrium constant for that process. We don't call it KEQ, though. We call it KSP for Solubility-Product Constant. So this is going to represent dissolving of an ionic compound. Remember that we leave solids out of equilibrium expressions. Because we're talking about dissolving a solid ionic compound, the reactant is always going to be left out because that's a solid. What we see is if you have a large KSP, that means the compound's very soluble. A small KSP means the compound's not very soluble. In the previous examples, we had chemical reactions and the equation was given to you because really there's no other way for you to know what it is. Here the equation will often not be given. Here we're looking at an equilibrium expression for barium sulfate dissolving. So the first thing you have to do is write the equation. You show the solid compound in equilibrium with its dissolved aqueous ions. So barium sulfate, solid, and then over here we're going to separate the ions. We've got Ba2+, and we've got SO4 2-. And you do need to balance this equation, make sure that you've got the correct number of everything. So this is our balanced chemical equation. And then we can use the same process of writing an equilibrium expression, except we're going to call it KSP instead.
Do you include liquids in this one?
Well, in KSP there won't be any liquids.
Oh, it's just going to be solids and...
It'll be solids and aqueous ions. There won't be any gases either. So it's the concentration of the barium ion times the concentration of the sulfate ion. Normally this, if this wasn't a solid, it would be divided by that, but because its concentration can't change, we leave it out. So the KSP expressions are not going to include fractions. So that's good news for some of you. How do you know what KSP is? Well, people have done experiments and compiled all kinds of data, and you can go look up the solubility-product constant for almost anything. So here's a table from your textbook. If you need a KSP on a test, I'll give it to you, but if it's in the homework or a worksheet, you might have to go look it up. So if we look at all of these things and compare these to the solubility rules that we learned before, which are more of a qualitative prediction of does it dissolve or not, you'll see that most of these are going to be in the does not dissolve category. Their KSP values are very small, meaning that only a tiny bit dissolves. So you can't actually say that a substance is completely insoluble in water, because that would mean that no ions dissolve. Practically insoluble, in terms of anything that you can observe, it could be insoluble, but there might be just a couple of ions that dissolve. And so the KSP is never going to be infinite or infinitely large, or it's never going to be zero, but it can be kind of close. Write expressions for KSP for each ionic compound. So here we have AgI. So we want to start with the solid ionic compound. AgI is a solid, and that is in equilibrium with, what are the two ions? Ag and I. Okay, so those are going to be aqueous. And they're going to have charges. 1. Silver is always +1, iodide is always -1. So group 1A, 2A, 3A, zinc and silver. Silver is always +1. You could figure that out even if you didn't remember that by looking at the charge on this. So KSP equals the product concentrations raised to a power equal to their coefficients, but the coefficients are 1 here. So it's just the concentration of silver ion times the concentration of iodide ion. We don't dissolve by the concentration of AgI because that's a solid. Solids are left out. Any questions?
How do you know this is a solid?
Because this is an expression for dissolving a solid ionic compound.
So the
KSP is a solubility.
reactant will always be.
It'll always be a solid. Calcium hydroxide. Well, you start with the compound, CaOH2, as a solid, and say, well, let's see what happens if we dissolve that in water. It's going to be in equilibrium, and we have to look at the ions. There's always two ions in Chem 3A. So there's going to be calcium, and there's going to be the other, hydroxide. Calcium has a 2+ charge. That'll be aqueous. Bless you. Hydroxide has a -1 charge. That'll be aqueous. And we have to make sure this is balanced. Is it balanced?
No.
No. There are 2 OHs for every calcium, and so I need a coefficient of 2 in front of OH. KSP, then, is the concentration of calcium ion times the concentration of hydroxide ion raised to what power? The second power. So there's the expression for that one. Any questions? We can use KSP to determine the molar solubility. Solubility, we've mentioned before, we talked about how many grams would dissolve in 100 grams of water. Molar solubility is the number of moles of a compound that will dissolve in 1 liter of solvent. So it ends up being a molarity. How many moles per liter of that compound will dissolve? We can calculate it from KSP, and it's usually abbreviated as a capital S. So capital S means how many moles will dissolve per liter, the molar solubility. Determine the molar solubility, S, of silver chloride. So here they wrote the equation out for us, and they gave us KSP. We need the equilibrium, or the solubility expression for this equation. Oops. KSP equals, that's a solid, that's not going to show up. We've got product times product, Ag plus times Cl minus. So that's what KSP equals. But we're supposed to find S, and there's no S anywhere that we can just like solve for, right? S is how many moles of silver chloride dissolve per liter. So here's where we have to do a little bit of thinking. We can't just follow a blind pattern. If 1 mole of this dissolves, how many moles of silver ions would there be? 1. And how many moles of chloride ions would there be? 1. Initially, we've got silver chloride in the beaker with water. There are no silver ions and no chloride ions. These are coming from the solid. They are always going to be in the ratio shown in the equation. It's like a pair of shoes. If you have 10 pairs of shoes and you take them apart into a left shoe and a right shoe, then you have equal numbers of left and right shoes, right? Because every box has 2 shoes in it, 1 left and 1 right. So if 1 mole of this dissolves in a liter, then the concentration of silver ion would be 1 mole per liter. And the concentration of chloride ion would be 1 mole per liter. Does that make sense? Mm-hmm. The number of moles per liter is the S. No, it's not 2. So if I have S moles per liter of the silver chloride that dissolve. That means that the concentration of silver is S and the concentration of chloride is S. They're equal to each other. It's not necessarily one. It's a 1-to-1 ratio. What I'm trying to get at here, not very effectively, is that the concentration of the silver ion is equal to the concentration of the chloride ion. Okay with that? And that will equal the moles of silver chloride that have dissolved per liter. It's the moles that dissolved. And what is that called? That's called S, the molar solubility. So I'm going to plug S in for the silver ion concentration, and I'm going to plug S in for the chloride ion concentration. So that's going to be S times S. We usually call that S squared. So S squared is equal to KSP. What does S equal then? It's the square root of KSP. S squared is KSP. I need to take the square root of this and the square root of that. Yeah.
So the only reason that the molarity of the silver and chloride are the same, chlorine are the same, is because the fact that the mole ratio is 1-to-1 for all.
Right.
So if you try to go from like n to moles back to n, you just get 1.77 times 10 to the negative 10.
Well, this is not the concentration of anything.
Oh.
This is the concentration of silver times the concentration of chloride.
Okay.
In this situation where we're starting with pure water and we're dissolving this, we can know that silver ion and chloride ion have to be in equal concentrations because they came together, right? So we know that those are equal. Now we've reduced it to one variable. We know what KSP is, and so we can solve for S. So it's the square root of KSP.
So what if it wasn't a 1-to-1 ratio?
We'll get to that. So what this tells me is that at equilibrium, the concentration of silver ion is going to be 1.33 times 10 to the minus 5 moles per liter. The concentration of the chloride is going to be the same. And that means that 1.33 times 10 to the minus 5 moles of silver chloride can dissolve in 1 liter of solution. That's not very much. That's why we say silver chloride is insoluble, because very little of it will dissolve. Any questions?
So,
Mm-hmm.
so when you see that, like you, moles ratio like one and one, can we just do like the square root of
Yes.
KSP without doing that?
Yeah, when you have equal numbers of these ions, you can just take the square root of KSP, and that'll be the solubility. Calculate the molar solubility of calcium sulfate. Well, it'd be a good idea to write the chemical equation describing how this dissolves. So calcium sulfate, a solid, in equilibrium with calcium ions and sulfate ions. So here we've got one calcium ion for every one sulfate ion. And so if you can remember, the molar solubility will just be the square root of KSP. I'm not real good at remembering things like that. I tend to want to just think it out over and over again. KSP is going to equal the concentration of the calcium ion times the concentration of the sulfate ion. No exponents because there's no coefficients. And I know that the concentration of the calcium ion is going to equal the concentration of the sulfate ion, because they came as calcium sulfate. So you could think of it, I mean, there's the shoe analogy, but you could think of it as couples coming to a fancy ball or something, and there's the man and the woman, and they come in and they're introduced by whoever the butler, and they come into the party, and then they separate and they mingle and they do stuff, but they came in pairs, so you have an equal number of men and women, right? Because they came paired up. They're not paired up anymore, but there's equal numbers. Does that make sense? They came together and then they split up and they're mingling, but there's equal numbers. So those are equal to each other. You could call that X, you could call it S, because that's what it is. It's the solubility. For 1 mole per liter of this that dissolves, I'll get 1 mole per liter of that and 1 mole per liter of that. That's just an illustration. We're not actually going to multiply those, but we're going to call this S, and we're going to see that S is equal to the square root of KSP, because this is S squared, S times S. What's KSP for calcium sulfate? I don't know. I don't expect you to know that. How do we find out? Well, go look in the table. Here's this lovely little table, calcium sulfate, 7.1 times 10 to the minus 5. (7.1) times 10 to the minus 5. Was that 7.10? I kind of think it was. Yeah, it was. Okay. So the square root of 7.10 times 10 to the minus 5 equals 0.008426. Yeah, that wasn't a 4 at all. That was another 2. 8426. 3 sig figs. So 0.00843 molar, or you could put that in scientific notation, 8.43 times 10 to the minus 3rd molar. Calcium sulfate is not very soluble. Any questions? The examples that I did both had a 1-to-1 ratio of the cation and the anion. On an exam, that's the only sort of thing that's going to happen. On the worksheet, there may be some that are different, but it does make things a little hairy. So I'll just warn you about that, but it won't be on the exam.